So what we have here are two small spaceships, each of mass m equal to 2000 kilograms, that are moving in a circular Earth orbit at an altitude h of 400 kilometers. And we're told that Zap, the commander of one of the ships, arrives at any fixed point in the orbit 90 seconds ahead of Blip, the commander of the other ship. Now, there are a bunch of questions, and each one very nicely covers some concept around satellites and orbits. So the first question is to find the period T0 of the spaceships. Now we know that the time period of both the spaceships must be identical, since their orbital radii are the same. Also, their orbital velocities are also equal, because for any given orbit, there is precisely one specific orbital speed at which a satellite can remain in stable circular motion. So here the orbital radius is r is equal to 6.77 into 10 to the power 6 meters. Then using Kepler's law and plugging in the values which we know, the time period equals 5.54 into 10 to the power 3 seconds. The next question is, what is the speed of the ships? Now, since we've already calculated the time period of the ships, all we need to do is divide the circumference of the orbit by the time period. That is, V0 is equal to 2 pi r upon T0, and this equals 7.68 into 10 to the power 3 meters per second. For the next question, at point P, Commander Blip fires a burst in the forward direction that reduces his ship's speed by 1%. And post this burst, the spaceship follows the elliptical orbit like this. And we are asked to find the new kinetic energy. So the new kinetic energy would be half m into 99% of V0 square, which when you calculate equals 5.78 into 10 to the power 10 joules. The next question is, what is the potential energy of Blip's spaceship immediately after the burst? So the potential energy remains the same as it was before the burst, because the r value has not changed. So U equals minus g into m Earth into mass of the spaceship divided by r, which when you put in the values equals about minus 11.8 into 10 to the power 10 joules. The next question is, what is the total energy of Blip's spaceship? Well, the total energy is nothing but the sum of kinetic and potential energy, or E is equal to K plus U, which when you put in the values equals minus 6.02 into 10 to the power 10 joules. Next, we have to find the semi-major axis followed by Blip's spaceship. So we know that for elliptical orbits, E equals minus gm Earth into m upon 2a. That is, we can replace r for circular orbits with a, the value of semi-major axis. So a equals minus gm Earth into m upon 2 times capital E, or the mechanical energy of the spaceship. And when you put in the values, this equals 6.63 into 10 to the power 6 meters. The next question is, what is the orbital period of Blip's spaceship now? So the time period of a satellite moving in an elliptical orbit is given as t is equal to 4 pi square a cube upon g times m Earth. Then putting in the values which are all known, we get orbital speed equals 5.37 into 10 to the power 3 seconds. The next question is, by what time will Blip reach point P sooner than Zap? So the difference between the time periods of the two is now delta t is equal to T0, which was the original time period, minus t, which equals 5.54 into 10 to the power 3 seconds minus 5.37 into 10 to the power 3 seconds, which equals about 170 seconds. That is, Blip is faster by 170 seconds, but since he is 90 seconds behind, Blip will arrive back at P ahead of Zap by 170 minus 90, or 80 seconds. So the key takeaways in this problem and the solution are that the orbital radius fixes speed and period. Same orbit means same speed and time, regardless of the object's mass. 2. Small changes in speed shift the orbit. So we saw even a 1% velocity drop transforms a circular path into an elliptical one with a shorter period. And 3. Energy tells the orbit's story. The satellite's total mechanical energy directly determines the shape and the duration of its orbit.